All right, here we are in the section 2.2. This is our last one for week 3 over the summer session. So this is on more things to do about characteristics on functions and their graphs. We're also going to get in some increasing, decreasing. We're going to get in some even, odd, neither. We're also going to be looking at the piecewise function as well. So let's dive into this. There are other features of a function which we will talk about in this section. You should be familiar with the words decrease, increase, maximum, and minimum. We will now be looking at these words in terms of a function. So, a function is increasing and I'm just going to kind of give you the mathematical version of that, but then we'll talk about it graphically. On an open interval I, if f of x sub 1 is less than f of x sub 2, where x sub 1 is less than x sub 2. So basically that means that if I have two x values that are one that's smaller than the other, then the function value of the one that's smaller is also smaller than the function value of the number that's larger. Now, if a function is decreasing, meaning down, going down, on an open interval I, then f of x sub 1 is going to be greater than f of x sub 2. You would think it would be kind of reversed, but it's not if x sub 1 is less than x sub 2 again. And a function is referred to be constant on an open interval I if f of x sub 1 equals f of x sub 2. Okay, so here right below us are some pictures that show when a function increases. So here when x is less than x sub 2, x sub 1 is less than x sub 2, then f of x sub 1 is smaller than f of x sub 2. So this is when they're increasing. And again, graphically, I like to be able to see it myself. We're going up from left to right. Here, we're going down from left to right, hence it is decreasing. So here, the smaller values function is bigger than the larger values function, and that is a decreasing. Constant means we're just going to stay the same. Okay, it's all going to be flat. Okay, so think about if you're walking up a mountain. If you're going up, you are increasing the mountain. If you're going down, you're decreasing the mountain. Again, it's all from left to right, just as if you're reading a book. All right, so let's determine the intervals on which the function is increasing, decreasing, or constant. And these intervals are in terms of your x's, okay? So you have to look left to right and figure out, according to the x values, when is it going up, when is it going down, and when is it going up again in this case. So I'm going to kind of highlight this. It's going up to here, and then I go down, and then it starts here, and I go up again. So I need the x values at which that is true. Now, we are not going to determine an inclusion or an exclusion of that, so we're just going to do all open intervals for this, and we're going to do interval notation. So from negative infinity on all these x's, I'm going to increase until I get to this point, which is the x equaling negative 1. So increasing, we're going to go from negative infinity to negative 1. And then I jump over from negative 1 to positive 1, and then from 1 on, so again, if I'm over here, I'm way up here off the chart, okay? But from positive 1 to infinity, we keep increasing as well. So positive 1 to infinity, there's two separate intervals there. We're going to combine them with that u to represent union. Now, the only other place that we have a piece of our function is this piece right here. Well, left to right, it's going down. And what are the x values that it's going down from? Well, it's from negative 1 to positive 1. And again, that's going to be our interval. Looks like an ordered pair, but it is actually an interval. And so we've covered everything on our function. Therefore, there is not anywhere where we are constant. Okay, so this was a strictly increasing and decreasing function. Now, if I look at this guy right here, and I go from left to right, and I start here, and it looks at what it does. It keeps going and going and going. It goes up, 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 and it does not ever come down. So this, actually starting at negative 1, is an increasing function always. So from negative 1 to infinity, we are going to be increasing. Now at that point, you're not increasing or decreasing, so we're not going to put a bracket here. Now since that's an ever increasing function, there's no decreasing, nor is there any constant. Okay, so you could write none or you can write not applicable. I'm not sure how MyLab Math will ask you for that, but let's look at this next function. This next function, starting again left to right, notice what happens. Ooh, we're right here. We're all the same. It's a nice flat piece. It's constant. And we're also constant over here. So let's talk about from negative infinity all the way up to this x value, which is actually at -4. So we're going to be constant from negative infinity to -4. Again, you don't have to include those. Make sure you put a parenthesis there. And then I'm going to skip over until I get to this x value, which is at x equaling 2. And from 2 to infinity, we end up having more constant function at that point. So I'm going to go 2 to infinity. Again, separate that by my union. Now, what's happening in between here? What's happening in between here is that we are going down, down, down. From here, left to right, I'm going down, and I'm continuing to go down at that point. So this is decreasing from this x value of -4 until I get to this x value of 2. So from -4 to 2, we are decreasing, and unfortunately, this function, we don't have any increasing parts, so that would be not applicable. Okay? All right, so make sure you go left to right and you use only x values. And we're not even really looking at the y values at this point. We're looking at x values for that. Okay? All right, very good. Now let's talk about relative max and relative minimum. If I have a maximum, it's like a high point. If I have a minimum, that's the lowest it can be. So we're going to also look at that in terms of a function. So the point at which a function changes, its increasing or decreasing behavior, can be used to find a relative max or a min. Sometimes these are called local maximums and minimums, or relative maximum. They're the same thing, okay? So different books and different times will say the opposite or the different things. So on this function that I have here, I'm decreasing, and then I start increasing again. That is a case where I end up having a minimum, a bottom out point. That would be my relative min. Then if I increase here and then I come back to decreasing, that's where we have a maximum. So let's look at this graph that I have here. I have it graphed. It looks like it's been graphed on a graphing calculator. Here's the function that was used to graph that. And what I should say are that relative max and mins, they are actually y values, okay? What is the minimum? You're going to say, what is that y value? That's the bottom out point, when x equals something, okay? So, numbers for the max or min. So, oh, wait, for the max. We want to use the graph to find the numbers, if any, at which the function has a relative max or min, and what are these relative maximum and minimum. Okay, so here we're looking at the max first, okay? So the max occurs when we go increasing then decreasing, so it's going to occur right here, and I'm going to let that occur at x equaling 1, okay? Numbers for where we have a max, that is when you want to put x equaling 1 there, so you are reminded. But when I ask for what is the relative max, now, I don't know exactly what this is here, but that function is going to be able to give me that output, okay? The other values we were able to see, but they don't give it to me here, okay? So what I need to do is I need to put that x value into that function and figure out what that is. So I need to do 2 times 1 cubed minus 15 times 1 squared plus 24 times 1 plus 19. Now, with 1, that's very nice because 1 cubed, 1 squared, and anything times 1 is going to be itself. So this is a 2 minus a 15 plus 24 plus 19. And when you do that, the value that you get is 30. That's where the max is going to occur at x equaling 30, or excuse me, y equaling 30 when x equals 1. Okay, now let's change directions and find the minimum that they're asking for. Notice we increase and we decrease, but what minimum occurs when we decrease and then we increase. And that's going to occur right here at 2, 3, 4. So at x equaling 4, I have a minimum. And what is that minimum going to be? Now, we're going to use this here. We have to take x equaling 4 and plug it into that function. So I need 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 plus 19. Now, order of operations, I must cube that 4 first, which is 64 times 2 is 128 minus 4 squared is 16 times 15 gives us 240. 24 times 4 is a 96 plus 19. So if I run that through, use your calculator if you need to, the minimum value is at -7. Now, the reason I did this one is because you want to make sure that you use that function because you don't have any points on there, and this one's not as nice to figure out what it is, but you can use the function. Now that one, I don't know, I don't necessarily like that graph on that for that because it should be dipping below. If it's a negative number, it should be down here somewhere, but we're going to go off the function, not by what the picture looks at. Okay. All right, very good. So those are max and mins. If it's obvious on the picture, you don't have to plug it into the function, but if you don't know what it is, then you might need to plug it into a function. Okay, now this part we're going to ease into do some symmetry, okay, and symmetry is kind of like a mirror. If you have a something that's symmetric like a parabola, if I have a parabola, remember x squared, f of x equals x squared z, so if I fold along this y-axis, that's my mirror, things match up, this matches over here. So that's what we kind of started with there. Symmetric with respect to the y-axis means that if I have a point x, y, and then this point would also be on there, and that's the point actually -x, y would actually match up with that. And in order to test for symmetry, we want to sub in -x for our x into our function, and we want to get the same equation. And when we talk about functions, we refer to this as being an even function. And when we get back the same function, it is going to look like that. So when you throw -x in for our original x, we get back the original function. That's what we're looking for. Okay? Now, if we are symmetric with respect to the x-axis, I'm just going to turn that parabola on its side because now we end up having symmetry over this being my mirror. And this, be careful, it's not a function, it's a relation, because if I try my vertical line test, it would cross it in 2 places, and that's bad. But we can still talk about symmetry. Now what happens is if I have this x value, then I have a y value and a negative y value. So x comma negative y is a point that's on my graph. And if I sub negative y in for y, then we get the same equation. Okay, now it's not going to be an even or odd function because this is not a function. Okay, now symmetric with respect to the origin. The best one I can show you is that x cubed, y equaling x cubed is one that's symmetric over the origin. And if I have, say, like this point is 2, 8, then this point over here, -2, 8, -8 also works. So if x, y is a point, then -x, -y is going to be a point on that graph. Now we're going to sub in -x for x and -y in for y. And if we end up getting that, then we end up having an odd function. And the odd function is if I throw -x in, then we're going to get the opposite of our function. So these kind of things, test for symmetry is a little bit separate than our even and odd functions. We're going to pretty much work with even and odd functions, okay? And so let's see some examples here. See if we can scroll that a little bit and stop there. Now, determine whether each function is even, odd, or neither, and also determine the symmetry of the graph. So if we determine even, odd, or neither, then we definitely can come back and say that that's symmetric to the y-axis and to the origin, okay? So determine whether our function is even, odd, or neither. So if I have this function, well, first off, this isn't a function, okay? So this is a neither, definitely, because we do not have a function there, okay? But do we have symmetry? In this case, I do have symmetry with respect to the x-axis. WRT is with respect to the x-axis. So there's the symmetry on that part, okay? Now, if I look at this guy here, looking at my points, I have the point 1, 4. Is it symmetric with respect to the y-axis? No, because I don't have a point over here. Is it symmetric with respect to the x-axis? No, because I don't have a point down here on that. But we are, if you notice, this has its opposites down here, and this guy has its opposites right here. So this one, I'm hoping that you tell me is going to be symmetric with respect to the origin. Origin symmetry, if you want to write it that way. And if we have origin symmetry and it's a function, that means we have an odd function. Okay, so making sure you have this chart, please make sure that you look at both. Okay, now unfortunately we don't have a graph for these next two, but what we're going to try to do is determine even and oddness by this, which means we have to evaluate at f of negative x. If I get back the original function, it's even. If I get back the opposite of the original function, then it's odd. If it's neither one of those, then it's neither. Okay? All right, so we're going to check f of negative x. This tells me I'm going to put in a negative x here and a negative x there. So I'm going to go negative x quantity cubed minus a negative x, and I'm going to simplify. Negative x times negative x times negative x is a negative x cubed. Negative times a negative is a positive x. Now, if I want to compare that to this, definitely they're not equal. They're not the exact same, so it's not an even function. But notice, this is positive, this one's negative, this one's negative, this one's positive. So they are exactly opposites of each other. Now, a way I could do that to prove to you, if I take out or factor out a negative, that changes the sign to make this positive and this one negative. Notice here I have the opposite of the original function. So I do have the opposite of f of x. Therefore, it is an odd function. So we are odd. And if it's an odd function, we are symmetric with respect to the origin. So symmetric with respect to the origin. Okay. All right, let's try this last one. This last one, are we even, odd, or neither? We want to look at g of negative x. So I'm going to throw in negative x here and square it minus a negative x. And so we simplify this now. Well, negative x times negative x is a positive x squared. And a negative times a negative is a positive x. And we're going to compare this with the original. The original is definitely not the original because this one's positive. These are positive and these are our opposites, so it's not exactly the same. Now, do I have a complete opposite? Well, notice these have the same sign and these have opposite signs. So in order for it to be odd, everything has to be opposites of each other. Therefore, this is a function that is neither. If it is neither, then there is no symmetry whatsoever. You would just put neither on that. Okay? So I know that's a little abstract in a sense, and you wonder why we're doing it, but sometimes in graphs and such, when you're looking at even and odd functions, there are things that you can check of. If you know it's an even function, you definitely know it has to be symmetric with the y-axis, etc. Okay? So make sure that you kind of buckle down and figure those out on that. Now, we're going to turn our attention to, before we go to piecewise functions, we're going to turn our attention to a graph that's given to us and kind of do a review of everything that we've done so far with this graph. So we've done this in section 2.1 where we looked at domain range intercepts. Then we're going to add on our increasing and our decreasing and our constants and our relative max and mins. Actually, there's no mins on here, but there could possibly be a relative min because of this guy right here. and then evaluating some functions. So let's dive into it. Now our domain from last section, from left to right, we're looking at, notice here we have arrows, keep going and going and going. Therefore, for every x value, you do have something on that function. Our domain is from negative infinity to positive infinity, or it is that funky R, all real numbers. Now, the range, we're looking from down to up. Domain left to right, range down to up. So there are values down here, and it keeps going. So I have all kinds of values down here, and I keep going, I keep going, I keep going, and the highest one I can get to is right there at that point, which is a y value of 4. So that means I go from negative infinity, and I maxed out at 4. Negative infinity to positive 4, including that with a bracket. Now, are there x-intercepts? Go along my x-axis. Bam, there's one, here's another. So therefore, negative 4 and 4. I have multiple ones. And do I have any y-intercepts along the y-axis? Bam, there's a y-intercept, which is at y equaling 1. Now, let me get rid of all this, because now we're going to determine where our function is increasing and decreasing. So, where are we moving up, left to right? Well, here we're increasing, increasing, increasing until I get to there. Then I go down, and then I start going back up slightly, and then I go down. So let's worry about the red. So everything from negative infinity is going to be increasing from left to right until I get to this x value, which is negative 2. So I'm going to go from negative infinity to negative 2. Again, these you don't want brackets, you just want parentheses. And I also have another spot right here that I'm increasing. So what x values are those? That's from 0 to 3. So from 0 to 3, I am increasing, and I'm going to union that. Then we need to determine where we are decreasing. So from here to here, from negative 2 to 0, we are decreasing. And from here to here, and it keeps going, 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 we are decreasing forevermore. So here we're starting at 3 to infinity. Now, you should, in all those cases with increasing, decreasing, and constant, you should get everything from negative infinity to positive infinity. If you notice, we're going to go here, then 0 to 3, then 3 to infinity. So we got everything, therefore meaning that this constant doesn't occur anywhere on that function. Okay? Now, where is the numbers of relative max? Relative max. That means places at which we maximize out. So notice here, hopefully you can see 2 of them. There's this one here, and there's that one there. Okay, now the one I did above was I had to give you the function, but these are nice because we know that that occurs at 2, and this one occurs at y equaling 4. But what are the x's? Now, if you need to write the points, go ahead and do so. This is at 3, 2. Okay, so the numbers of the relative max, they're looking for the x's. So it's at x equaling negative 2. And we also have a relative max there at 3. Now, what is the relative max and mins? Well, we have 2 of them, right? We have the relative max is at 4 and at 2, when x equals negative 2 and 3 respectively. So at 4 and 2. Very good. Okay. All right. So that was from this section. Our last section, we did these types of problems where is f of negative 2? I'm looking for the y value when x equals negative 2 is what that's asking for. So I look over where negative 2 is for x equaling negative 2, and I go up to here. Well, what is the output value when x equals negative 2? It is at positive 4. And we want to know where the y value equals 0. Well, where's the y equaling 0? 0 is right here for the y value. I want to look across that function at where y equals 0. This is another way to ask for the x-intercepts. We already talked about those as negative 4 and 4, but using a function notation, that's good for you to see that. Okay? Now, is this function even, odd, or neither? Even function was symmetric over the y-axis. If I fold over the y-axis, things don't match up nicely. If I look at being symmetric over the origin, which is an odd function, then notice this is the point 3, 2. Is the point -3, -2 on there? -3, -2 is this point right here? No, it's not on that function. Therefore, it's not odd either. So we are neither for that function. Okay? All right, very good. Let's turn to our last little piece in this section, and it is dealing with what we refer to as piecewise functions, where we are piecing things together. So a function that is defined by two or more equations over a specific domain is called a piecewise function. I messed that up. Piecewise, let me redo that. All right, piecewise function. And here's an example of that. And so the first thing they're going to ask you to do is to kind of evaluate that function at certain values. Now notice here that I have f of x is equal to 2x minus 1 if my x value is less than 0, and I'm on this function, negative x plus 2, if I have an x value that's greater than or equal to 0. So when I'm evaluating that function at -3, I have to determine which one of these inequalities that it lies. Well, -3 is less than 0. So that would mean that I have to plug -3 into the corresponding function, which is this. So that means I need to do 2 times -3 and then subtract 1. Well, 2 times -3 is -6. Subtracting 1 gives me -7. Now, the next function that we need to look at, or the next problem, is f of 0. I need to know which of these inequality that 0 lies in. And now here's the 0, it's the breakpoint. So you have to be very cautious of where that equal stands. So it's in this one right here. Therefore, I need to throw 0 into this function to evaluate f of 0. So negative of 0 plus 2, well, negative of 0 is still 0, plus 2 gives me a 2. So f of 0 equals 2 here. And I need to determine where f of 4 is. What is f of 4? F of 4 is greater than or equal to 0. Therefore, I must put 4 into that function. Do the opposite of 4 plus 2. Therefore, f of positive 4 is -2. Okay? Now, make sure you put the x value in the correct function, okay? And now we're going to actually, and these actually are just in disguise some points that we have on our graph, but we are going to graph this function, this piecewise function, and I'm going to do so by choosing some values that are less than 0, choosing some values that are 0 and above, okay? So I'm going to choose for the first function values that are less than 0. I'm going to choose -1, -2, -3. And I'm going to plug it in, okay? I'm going to plug it into this corresponding function. 2 times -1 is a -2, minus 1 is -3. -2 times positive 2 is -4, minus 1 is -5. -3 times 2 is -6, minus 1 is -7. Okay, so if I graph that, -1, -3, -2, -5, and -3, -7 is off the chart. So I want to actually add in 0 here too, okay? I know 0 is not equal to on that one, but 0 is kind of the break point, because I could choose 0.5 if I wanted to. I could go all the way up to 0. If I throw 0 in there times 2 minus 1 is a -1. So if I were actually at 0, I would be at -1. Now to symbolize that it's not equal to, I'm going to put an open circle there, okay? And so you actually need to include that breakpoint. I should have done that from the start. All right, so I'm going to connect those. That's actually a line, not 2x plus 1 or minus 1, but powers of 1. These are both going to be straight lines, okay? Now, let's turn our attention to any values that are greater than or equal to 0. If you want to do them by t-chart, please do so. So we're going to see if we can see what it is. Well, let's go ahead and do 3 as well. So if I throw 0 in, now we're at this function. So I'm going to put 0 into this function and add 2, I get 2. When I throw 1 in there, negative 1 plus 2 gives me 1. If I put 2 in there, negative 2 plus 2 is 0. And if I put 3 in there, negative 3 plus 2 is a negative 1. Now, remember, at 0, this one we are equal to. So we're going to put a solid dot here at 0, 2. That gives me that point. 1, 1 is my next point. 2, 0 is my next point. And 3, negative 1 is my next point. And I'm going to connect those for that line. And that right there is the graph to our piecewise function right here, where it's made up of 2 different lines. And we're piecing that function together. So at my y equaling, or my x equaling 0, to the left we're on the line 2x minus 1. And to the right, we're on the line negative x plus 2. And so that is our piecing of our graph together. So I think at the start here, it's easy just for you to kind of use some t-charts here to determine what the graph is going to look like. Okay? And our last problem for today, we're going to look at graphing this piecewise function. Notice I have an x squared plus 1, which I hope you remember is of a U shape for a parabola. And this is a line, and it has a negative slope, so it's going to be a line that goes like this. And we're going to piece those together around the breakpoint of x equaling 1, okay? So I'm going to start with a t-chart. I'm going to choose values for this parabola for x values that are less than 1. Now, it's not equal to, but again, I want you to put that 1 in there because we're going to do an open circle at that point. So I'm going to choose values that are less than that. So 1, 0, negative 1, negative 2. Let's see if we can find our parabola that way. Throw that in. 1 squared is 1 plus 1 is 2. 0 into here. Squared plus 1 is 1. Negative 1 squared is positive 1 plus 1 is 2. And negative 2 squared is 4 plus 1 is a 5. Let's graph those. Again, this one is an open circle because we are not equal to. Over 1 and up 2 gives me that point. 0, 1, negative 1, 2, and negative 2, 5. Do you see that U shape forming? Now, if I just had that x squared plus 1 by itself, I would graph this entire piece, but I don't. I'm only less than 1 here. So I have to just graph that part of it. That's the piece I want for that. Now, let's do the other function, negative x plus 3, and I want for values that are greater than or equal to 1. So let's go 1, 2, 3, see if we can find our line there. So, if I throw 1 in here, negative 1 plus 3 is 2. Throw 2 in there, negative 2 plus 3 is 1. Throw 3 in there, negative 3 plus 3 is 0. So at 1, 2, oh look, they actually match up this time. So because this is the equal to, I'm going to go ahead and put that solid dot for this graph, okay? Over 2 and up 1, over 3 and none in the y direction. It is a line, so I'm going to connect those points. You could put in 4 and 5 if you want, but this here is my piecewise function. Again, to the left of negative 1 is a parabola. To the right of 1, did I say negative 1? Sorry. To the left of 1 is a parabola. To the right of positive 1 is that line. And that is the graph of our piecewise function. Oh, whoops, I forgot to state the range. Did I ask that on this other one? Let's go ahead and graph the function above and find the range. Oh, let's do the range on both of those, okay? So the range, remember, is our y value. So I'm going to start from bottom to top, and I'm going to figure out, okay, I have y values here, I've got y values here. Even though I don't have a y value there, I do have one here. I've got y values until I stop right here. So the range on this function is going to be from negative infinity all the way to the top out at 2. And include that. Now, what is our range of this guy? Well, from negative infinity up, this guy keeps going forever and ever and ever. So I've got y values, and I still have, even though there's multiple ones, that's okay. And I still have y values, and this symbolizes it's going to go on forever. So the range of this function, I hope you're screaming at me, is either the all real numbers, or you can write it in interval notation like that, from negative infinity to positive infinity. Okay? All right, very good. So diving into some functions, we're evolving. We're getting used to these. Hopefully remember and seeing some shapes. We're going to be able to use that increasing, decreasing, max, mins, domains, and ranges, all of those things. So make sure you practice those so you can keep them straight. Until next time.